Okay, let's continue with example 3. Find the volume of the solid obtained by rotating the region bounded by the parabola x minus x squared and y equal to 0. Then rotate about the line, the vertical line, x equals 2. Let's show the region. Okay, let's draw the region first. Not good. So for this parabola, okay, how can you draw this parabola? Y equals x minus x squared. So you can start with y equals minus x squared. Minus x squared, which means you reflect about y equals x squared about x-axis, about x-axis. So in this way. And then you can get minus x squared plus x plus 1/4, right? And then plus, you put this part inside, okay? Sorry, here should be minus. Here should be minus. Yes, here should be minus, and then so that is the parabola minus x inside is x minus 1/2 and plus 1/4, right? So that means the vertex shift to 1/2 and 1/4. Okay, this is 1/2, and here is 1. Okay, here is 1/2 and 1/4. So the parabola will be looking like this one. It will shift minus x squared. It will shift minus x squared. So starting from minus x squared, it will shift 1/2 to the right. Okay, 1/2 to the right and 1/4 to the upward, right? 1/4 upward. And you can solve this equation also. You can solve this equation, let it equal to 0. Then the intersection, let it equal to 0, which means the intersection with the x-axis will be 0, 0, and 1, 0, right? So this point is 0, 0. This point is 1, 0. That is the intersection with x-axis. So we get this parabola, and this parabola, the region, this part, and I think it should be x-axis, not y-axis. There is a little problem. So should be this part, and oh yes, y equal to 0. Yes, y equal to 0. That is the horizontal axis. So should be this region. This region rotate about the line x equals 2. X equals 2 is another vertical line, right? Another vertical line, x equals 2. So one student asked, how can we start the x minus x squared to obtain the curve of this one when we starting from minus x squared? So you just rewrite this polynomial, this x minus x squared as a complete square in this way. So that means you shift minus x squared parabola 1/2 unit to the right and 1/4 unit upward. So this parabola can be obtained. Okay, then we shaded this region. This region is obtained. Let me just denote the curve. The curve is y equals x minus x squared. And then this region will rotate about y-axis. Okay, will rotate about y-axis. And be careful from 1 to 2 here. This part is empty. Okay, This part is empty. So it's kind of ring, or it looks like a donut. Maybe you can call it in that way. I think somehow it looks like a donut, the solid. Looks like a donut. How can I spell donut? I don't know. Donut, this one. So looks like a donut, the solid, because this from between 1 and 2, this is the ring. Okay, this is the empty ring inside. Now here shows the solid actually. So from this is the rotating vertical line, rotating vertical axis, x equals 2. So that will be 0 to 1, this parabola, this region. 0 to 1, when they rotate about this x equals 2, so that becomes 3 to 4. Make sense? So that is 3 to 4. Now in this way we still need to figure out, okay? We still need to figure out what is the radius, right? What is the radius and the circumference, and what is the height? So again, okay, again for the ice, so here for this region you can obtain the ice approximating rectangle, okay? The ice, you can take it, the ice approximating rectangle is rotating, right? You can write the same statement. The ice approximating rectangle is rotate about x equals 2, and then the ice shell is obtained, right? So this is like we have this one, okay? This one, the ice rectangle. And then how about the radius this time? How about the radius? So be careful, okay? Be careful. Here the radius, you will notice that the radius will be this one, right? Will be this one from 2. So if you have this point is xi bar, this one is xi bar in the ice interval, so that will be this radius. This part gives the radius, and we know this part is xi bar if we use our notation, okay? Xi bar, if we consist with our notation, so this radius will be 2 minus xi bar. Of course, the conference is 2 pi times these radius. So the radius change. The radius is not always the xi bar, okay? And then how about the height for the ice shell? How about the height? The height again, it's a function value, right? It's a function value, no problem, okay? This one we only have one function. It's between, you can also take it as the top curve minus the bottom curve, but the bottom curve is y equal to 0, right? The bottom curve is y equal to 0. So the top curve will be xi bar minus xi bar square, right? Xi bar square. So the ice shell's volume, the ice shell's volume will be 2 pi radius. Now my radius is 2 minus 2xi bar, then times fxi. What is the height? What is the function value? So this one gives the function value, right? This one gives the function value. And that is the ice shell. So the V can be expressed as a definite integral. Check the region here. Check the region. It's starting from 0 to 1, right? It's starting from 0 to 1. And then 2 circumference, okay? So now it's not always 2 pi x fx because my radius change. So it's better to use the more general formula. Circumference, okay? Circumference will be 2 pi r. Now what is my r? R is 2 minus x. Sorry, should be x, right? When we write in the definite integrals, should be x. So will be 2 minus x. Then what is my function fx? My function is x minus x squared, this function, right? And don't forget the dx term, okay? The dx term. Then we can move the 2 pi as a constant outside, and then the polynomial, okay? The polynomial. So the volume of the given solid will be evaluated in this way, and you get a polynomial, okay? Get a polynomial, then find the antiderivative. Finally, we get the solid of this donut is pi half, okay? Pi half. So understand the rotating axis change, okay? Rotating axis becomes another vertical line rather than x or y axis, okay? So I also give those examples, okay? I also discussed those examples. So that will be all the examples we discussed for the cylindrical shells method. So always understand the formula. The volume formula is circumference times the height times the thickness, okay? So that is the section 3, volumes by cylindrical shells method. And we will try the quiz at the end of the class, okay? Then we will start the physics topic, section 4, work, okay? Work. And I think most of you already understand what is the work in physics, right? So according to Newton's second law, let's check the scenario. Okay, let's check the scenario. If an object moves along a straight line with position function st, right? We are familiar with the position function st. Then the force F on the object, we assume if it's in the same direction, okay? In the same direction, and according to the Newton's second law, the force will be ma, right? Force equals ma. And what is my a if we know the position? So the a is the acceleration. Acceleration is second derivative of the position function with respect to t. Right here, this s still means the position function. Okay, position function. And we understand the unit for the force, right? The unit for the force, we will call it Newton, right? Unit for the force. 1 unit actually equals 1 kilograms. Sorry, it's not times. Okay, it's equals 1. It equals ma, right? So should it be kilograms? The acceleration should be meters per second square, right? Meters per second square. So they are equivalent, right? That is the unit for the force, and we call it Newton. And we understand the force equals ma, right? Equals ma. If we know the position function, we can take the second derivative to work out the acceleration, right? This is pretty easy in physics. Now, let's check simple examples. And by the way, let me just write, if we know the force, okay? If we know the force, and I will write in this one, okay? I will write in this way. If a if the acceleration a is a constant, so f is also a constant, right? If the acceleration a is a constant, f is also constant, and the work done to remove the work done is to move the object for d distance, okay? For the distance d, so we can use the w, okay? W to denote the work. That will be the force times the distance, right? So here the W means the work. The F is the force applied on the object, right? Force applied on the object. And the D is the distance the object moved. And there is no problem to understand this work formula, right? Force times the distance the object moved. So here is the case when the force F is a constant. F is a constant, which means the acceleration is a constant, right? So that is pretty easy. We can use this formula to check those two questions. Okay, very simple question. Okay, so let me teach you some physics knowledge here. How much work is done in lifting a 1.2 kilograms book off the floor to put it on a desk that is 0.7 meters high, and use the fact that the acceleration due to the gravity is 9.8 meters per second. So here the gravitational acceleration is a constant, right? Is a constant. And when we lift the book, we we only we only take the gravity into consideration. Okay, only take the gravity into consideration. So we lift this book off the floor to put it on a desk 7.7 meters high. So the force, okay, the force you will apply on the book, right? To lift the book, you should give the force, okay? You should give the force which is equal to the gravity, right? Which is equal to the gravity of this book. So will be 1.2 times 9.8 Newton, right? Newton. And then the distance. Distance, be careful. It's distance. It's not the position. It's not the position change. Just the distance we move in vertical direction. We lift it to a desk 0.7 meters. And then the work, right? How much work? The work will be FD. It's pretty easy, okay? It's pretty easy. And I think we all understand the unit for the work should be joule, okay? Should be joule. So 8.2 joule, okay? 8.2 joule. And what is the unit for the work? The unit for the work should be Newton meter, right? Newton times meter, unit for work. And one, let me just check it. 1 Newton, okay? 1 Newton meter equals 1 joule. So 1 Newton meter equals 1 joule, okay? And the joule, from physics, we understand the joule is the unit or measurement for the energy, right? For the energy part. So that is the energy you consumed. Okay, you consumed to lift the book. So that is 8.2 joule. And from here we notice that the acceleration is a constant 9.8. So that makes the force is always a constant. You always use this force to lift the book. Part B. How much work is done in lifting a 20-pound weight book 6 feet off the ground? Okay. Maybe some books. Let me just call those books. Okay. So here we use the American measurement. Okay. The pound-feet, okay, pound-feet. And this one is very direct. The work will be, the pound is already the force, okay. The pound has already gives the force, so that will be the 20 times 6. So we get 120. How can we call this measurement? This is called the feet pound, okay, according to our textbook. This is called feet pound, and there is a unit change, okay. So 1 feet pound equals 1.36 joule, okay, 1.36 joule. So you can do that 120 times 1.36 joule, okay. So this one, the feet pound is the one used in American, okay, since our textbook come from American. So that is the one proper used. Just and I think you all understand there is a um there is a identity between feet and meter, between pound and the kilograms, right? Between the kilograms. So that's why we convert in this way. So 1 feet pound we call 1.36 joule. So just in case you might have some questions, okay, some questions with this unit, feet pound or joule, okay. So that is pretty easy, and that is not the topic we will focus today, okay. That is not the topic, because here the calculation is pretty simple. It's nothing with the integral, right? It's nothing with the integral we are deal with in this chapter. Now, let's check this situation, okay? Let's check this situation. When the work, we are going to work out, we are going to find the work required when the force is a variable, okay? When the force is a variable. For example, if the force is a function, okay? If the force is a function fx, it's not a constant anymore. So let's check this scenario, okay? Suppose that the object moves along the x-axis in the positive direction from A to B, and at each point x between A and B, a force Fx acts on the object. So where this F is a continuous function, that means this force will change, okay? This force will change. So we can define this as a positive function. So on the x-axis, so that will be, let's call it from A to B. And you can also draw a curve to denote your force, okay. You can also draw a curve to denote your force, like, so suppose this is my force function fx, okay. This is my force function. Then you will notice that at a different position, the force is different. So you cannot use you can't use the formula F times the distance to work out. So here the A is the starting point, okay, starting point. So it can be like the moving of this object, the object starting from here, okay. And in the ideal situation you can abstract your object as a point, okay, as a point. That is the way usually we do in the physics, okay. And why you can take it as a point, so check your knowledge in the physics, okay. So for the object you can take it as a point to move, okay, a point. So an object that will be taken as a point to move, it will start to move from A to B, and we need to work out the work required, okay, the work required for the object moving from A to B. So we need to work out the work required for the work required to move the object from A to B. To move the object from A to B. Now we understand. You cannot use the F times B minus A. We know the moving distance D. The moving distance D is B minus A. There is no problem. But the force is the function. For example, at this point A and a little distance here, the force change, okay? And some distance here, the force change. So the force, if we call the force is the function fx, that means the force will be changed as the x varies from A to B, right? So you can take this one as the Riemann sum we did before, okay? We did before. So step one, subdivide the closed interval AB. Subdivide the closed interval AB into n, okay? Into n. I will explain why we will establish the framework in this way. Into n subintervals, okay? Into n subintervals. And then you will get x0 to x1, x1 to x2, and xi minus 1, xi, right? Until the last one is xn minus 1, xn. And we understand the equal weights for each interval is delta x, which is b minus a over n. We divided this whole distance from A to B into n subintervals, okay? Into n subinterval of the equal weights, right? Into n subinterval with equal weights. And we know the formula, right? Delta x. And we obtained the n subintervals, right? We obtained the n subintervals, and we know it's very small, right? The each interval are very small as we increase the number of n. So we can assume that the force, okay? Assume the force applied when the object moves in the each subinterval. Assume the force applied on the object in the each subinterval is a constant. Why? Because this subinterval is very small, okay? It's very small distance. What is the distance? The object is moved in the I subinterval, delta x, right? In the I subinterval, the object moves delta x distance. So in the I subinterval xi minus 1 to xi, the object moves delta x. I can mark it as di, okay, the distance in the I interval. So, and actually in each subinterval, the object moves this distance, right? Moves this delta x distance. And then assume the force Fx applied on the object in the each subinterval is constant. So what is the constant we can estimate? So the force can be approximated by So we assume it's a constant. What is the best estimation for the force in the I subinterval? Xi bar, or you can call Xi star. Okay, it doesn't matter. Okay, so let's use the more general notation Xi star. Okay, Xi star. What does Xi star mean? Xi star is the sample point, right? Xi star is the sample point in the I subinterval, which means you can choose any value. So we can take this one as a constant, and we understand actually in the I interval the force will change, right? Let me use a different color. So here in the I subinterval xi minus 1 to xi, and the object moves delta x distance. And then how can we get the constant? In this I subinterval, we assume the force, because it's a very small piece, it's a very small distance. We can assume the force is a constant. What is the good estimation for the force? So we can think about the sample point or the middle point. Okay, the middle point. What is the force? The force actually is the height, right? So you can take this one as fxi star. Okay, fxi star. So here the fxi star actually is the function value, right? It's a function value. So that is the force we will use. Okay, that is the force we will use. So from here you will notice that actually we know the function value will change from xi minus 1 to xi, but we can use the function value at xi star to estimate. Then what is the work? What is the work we required? So the work estimated by this function value at xi star. So the work required in the I subinterval will be WR, right? Will be WR. What is this WR? Will be the force in the I subinterval times the DI, the distance we moved. So what is this one? This is the function value xi star times delta x, right? So this is the force times the distance moved in the I subinterval. But how can we understand this one? The height of the function, the height of the rectangle times the weights. So actually the work required in the I subinterval, that is the area of the i's rectangle. Okay, that is the area of the i's approximating rectangle. So from here you understand that. Okay, you understand that the work required. So let me write here. Okay, let me explain from the graph. The work required in the I subinterval, in the xi minus 1 to xi, which is wi, right? Wi. That is the area equals the area. Let me write the notation. That is AI. What does the AI mean? AI is, shall we use the AI? Let's just call it AI. Okay. What does this AI mean? That is the area of the i's approximating rectangle, right? Of the i's approximating rectangle. Now, we need to we need to find the work. We need to find the work required when we apply the force Fx from A to B, what does that mean? So that is the work. Also denotes the area under the function curve from A to B. Okay, from A to B. So let me explain here. Okay, let me explain here. Now we get much closer. Okay, we get much closer. So the work Wi, okay, Wi is Fxi star times delta x, which is the rectangle area, the area of the ice-approximating rectangle. Then how can we get the total work of the object when we apply the force Fx from A to B? So it can be estimated, it can be defined in this way: the limit of the Riemann sum as n approaches infinity, Riemann sum of the Wi, right? Of all the works, you add all the works together. So that is the limit of the Riemann sum Fxi star times delta x. My I starting from 1 to n will approaches infinity. What is this one? What is this one according to the area under the curve function f? So we can define according to the definition of the integral. So we can define the work in this way. That is the definite integral from a to b fx dx. Now what is this fx mean? This fx is the force, right? This is the force. It's a function, right? So which means it's a force function of the position x, right? Of the position x. This x means the place the object located. Okay, that is the location to denote the object in that way. So it becomes much easier to work out the work when the force is the function. Okay, when the force is the function, just the definite integral. So it will be much easier. Okay, it will be much easier. And we will look at the examples next time. Okay, we will look at the example for this part next time. And we will try one quiz. Okay, we will try one quiz for cylindrical shells.